Patrick Hill, talking about comparative morphological analyses of impact melt rock emplacement in terrestrial and Apollo impact breccias to understand Suevite?
Yes.
Okay. Formation. All right, thanks.
Okay, so this is some work that Dr. Rosinski and I have been working on at the Center of Planetary Science and Space and Exploration as part of the Canadian Lunar Research Network, a survey node in Canada. Our ideal goal is to try and reconcile the fact that when we went and conducted the Apollo-era missions, our understanding of terrestrial impact craters was quite limited, and so we want to try and help the community by contributing the newfound knowledge that we now have and bringing it forward to the modern times. Lunar nomenclature for impactites is defined by Stoffler et al., and this quote from New Views of the Moon is in regards to an Apollo 17 Breccia that within the literature has 6 names in publications from 1974 to the early 2000s. So we're hoping by bringing terrestrial impact structure terminology and nomenclature, we can help out the lunar community. That being said, however, the terrestrial community also has some issues with terminology itself. The term Suevite is historically used to refer to an impactite from the Reese impact structure, and it's being complicated by the fact that it's now being applied over a broad range of spatial and geologic contexts. It's even been used within the Apollo collection. Early on within the Apollo samples, it was referred to, direct comparisons were made to the Reese crater. And so what we hope to do with this study is to better understand the formation of melt-bearing impactites and to make nomenclature accessible for all communities, as well as identify important melt-bearing morphologies that could be returned to Earth in future sample return missions. So for those who are not familiar with what a Suevite is, in essence it's a Polymict Breccia, meaning that it's made of Clast from various lithologies. It's within a particulate matrix, which means that it contains both melt and or clastic components, and it has clasts that stretch all ranges of shock metamorphism. This photo was taken this summer in the Reese is of the Suevite, and that dark swirl is what the impact melt component looks like. It's been inconsistently used across the terrestrial community at impact structures with melt greater than 90% area to those less than 1%. And so because the Reese is a unique structure, by using this term across different terrestrial craters, we've been implying different geologic contexts for this formation. So that being said, within the lunar community, we really see it appear in the definition for a fragmental breccia, where a designated type of rock with vitric or devitrified glass, if it is cogenetic, would be analogous to the Suevite. And so what we hope to do by studying these impactites with melt is to understand what the connection is between the lunar fragmental breccias and those with the impactites that we see on Earth. In doing so, we hope to better understand Suevite formation as well as impact breccias and the role of volatiles and melt production in the formation of these rocks on different planetary bodies. So the Apollo samples that we've been looking at are limited to the Apollo 14 site and the Apollo 16 site at North Ray Crater and the Fragmental formation at Apollo 14. The Apollo 14 site was originally proposed to be an ejector blanket derived from the Imbrium Basin and is being described as analogous to the Bunte Breccia and limestone breccias at the Reese and not equated to the Suevite Breccia. The Apollo 16 site was originally proposed and had lines of evidence for being the best case of Suevite and the Apollo collection, and so was our primarily interest for this study. We've been analyzing textural morphologies of melt within over 75 different impactites, and we continue to analyze more across 6 terrestrial craters. What I'm going to present here will focus on Mistastin Lake, and that's because Mistastin Lake makes a nice little analog for a lunar setting because it is a crystalline target rock, not a mixed target lithology like the Reese, which has a lower volatile content, making it a little more analogous to the Moon. The target rock is anorthosite. Its anorthite content is lower than the Moon, so it's not ideal, but it's still nice to have the similar lithology. And we have access to a huge range of impactites within our own collection. So the Suevite takes many different forms at Mistastin Lake. It occurs at discrete lanes, large formations, and also as dikes. And there's three main lithologies that I'd like to highlight now. So within the Polymict Breccias, we have a melt-pour phase. If this will work. Nope. So within the melt-pour Polymict Breccias, we see both anorthosite and melt class, but within the matrix, it's mainly clastic and lithic with no melt within the actual matrix as a binding agent. Within the melt-rich Polymict Breccias, we see both, again, anorthosite and melt-rich class. However, within the matrix, we do see melt and evidence of a crystalline matrix acting as a binding agent for these breccias. We also see class-bearing impact melt rock, where the matrix is defined by fine-grained crystalline texture and is host to class-rich but also class-poor breccias. Within the Apollo collection that we've sampled, we see two distinct groups, and that's the Polymict Breccias with a clastic matrix, as seen in the photo 1, and then Polymict Breccias with a melt-rich matrix, as seen in 2. The Polymict Breccias with a clastic matrix similarly have impact melt rock class as well as an anorthosite class. However, within that matrix, it is solely clastic and no evidence of melt acting as a binding agent. All of the North Ray craters fit into the melt-rich with the melt-poor Polymict Breccias. The Polymict Breccias with a melt-rich matrix, however, once again have anorthosite and melt-rich class. However, within the matrix, we do see glass and impact melt rock acting as a binding agent. So from pure observational data, we've been able to identify that there is some similarities between melt-poor Polymict Breccias and those Polymict Breccias from the Apella collection that have clastic matrix. And similarly, the melt-rich Polymict Breccias in Mistastin are also very similar to those with melt-bearing matrix within the Apollo collection. However, as I stated earlier, we want to try and avoid some simple just qualitative observation, and so we wanted to quantify this. And so we applied a semi-automatic digital analysis technique that allows us to create 8-bit images that we can analyze for textual information. So what we can do is we can take high-resolution scans, as shown on the left for this Suevite, and we can create an 8-bit image that extracts the phase that we are most interested in. In this case, we're most interested in the melt-rich rock. And so from this, we can get area, perimeter, circularity, roundness, and fractal analysis to get a sense of the complexity. And so for what I'm going to show for this presentation is just some quantitative analysis of sorting by comparing cumulative perimeter fraction to cumulative area fraction. We can get a sense of how well or poorly sorted a lithology a phase is. If it is well sorted, it should follow a 1-to-1 ratio slope, whereas as it gets more poorly sorted, it switches, the slope increases. And so what we see at Mistastin is that those melt-poor Polymict Breccias are very well sorted, following that 1-to-1 slope. And then in comparison, the very poorly sorted ones shift to a much higher slope. And then when we compare this to the Apollo's collection, we once again see that the samples that have no evidence of melt within the matrix are very well sorted, whereas those that do are very poorly sorted, similar to the melt-rich Polymict Breccias at Mistastin. And so what we've been able to show is that in addition to this, in complexity data, which we are still working on, the clastic matrices within the fragmental Breccias are very analogous to the melt-poor Polymict Breccias, and we can actually say that with confidence due to quantitative analysis. Similarly, melt-rich Polymict Breccias are very poorly sorted and very similar to the melt Apollo collection with a melt-rich matrix. This suggests that we have potentially two different formation mechanisms for these lithologies. And as we compare this to other terrestrial craters, we begin to see a similar pattern where lithic impact breccias, where melt is not involved in as a binding agent, show that well-sorted, less complex morphology of the class. Whereas when we look at, for example, the Reese and melt-rich Polymict breccias, those become very well-sorted and more complex. And so we have two distinct formation models, and what we hope to get out of this is that as the impact cratering process is ubiquitous throughout the solar system, that some of these mechanisms of formations translate across planetary bodies. And so these clastic matrix breccias are most likely equated to ejecta blankets of purely lithic, whereas the more melt-rich, melt-bearing Polymict breccias on the Moon, Earth, and Earth could be more equated to the formation of melt-bearing Polymict breccias at terrestrial craters. So I'd just like to take a moment to thank and acknowledge all the different organizations that allowed me to be here, and it's nice to represent Canada and the US. So thank you.
Great, thank you. So we have plenty of time for questions. Okay. I'm afraid I don't have any. Yeah, please do.
It went by a little bit quick, but you did show one slide with a melt particle that you referred to as potentially a melt binding particle. And so the question I have is, do you think that that was a primary impact melt particle, or was that simply an agglutinate that got caught up in the breccia, in which case the fragmental breccia would actually be a regolith breccia?
Right, so the, one of the things that we're going to be tackling, especially with the Moon, given that there is such a high bombardment rate, is sorting out the cogenetic nature of these melt phases within the matrix. So as you said, if it is cogenetic, then it would be more equivalent to an impact melt rock on Earth. However, if it is just another fragment or agglutinate that's been launched in, then yes, it would be more equivalent to a regolith, or even a lithic breccia on Earth, where you have another lithology getting incorporated in. It just so happens that on the Moon that would be melt from another impact. So yeah, that's something we're going to try and tackle. And I think chemically it might be the way we go about it, but we're still thinking about that issue.
Thank you. Okay, so